Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to talk about something really important in linear algebra called linear independence and dependence. But to start off, I want to do this problem related to the span. That's a concept that we talked about last time, and it's this idea of the set of all linear combinations of the vectors given. So, in this case, of these vectors right here. And if you want to just show something is in the span, then you just have to show what linear combination of these gets you those vectors. So, the first one, just one green, it's not too bad to see that u equals, just take one of the first, take none of these second vectors, and none of these third vectors, and that would do it, right? If you want to show v, then you could take just one of the first, and then you could take minus one. Let me do that again. Nope, sorry. I wanted to do minus one of the first, and then plus u plus v. So I can cancel out the u's, right? And then I'm going to take 0 of the last vector, u plus v plus w, and that would do it, right? Because these will cancel out the u's, and then I don't get any of these anyways, and then I just get v, right? And to do the last one, to show w, you would just want to take 0 of the first one, and then you could take minus 1 of u plus v, and then if you add 1 of u plus v plus w, then you'll cancel out the u and v's from here, and you'll be left with w, right? But that would show that these vectors u, v, and w are in the span of these ones right here. So, linear dependence. Typically, this is actually how you see the definition. You're going to see it linear dependence defined, and then the definition for linear independence is simply them just throwing the word not in front of it. So any set of vectors that don't do this thing up here that I'll explain is called linearly independent. And this is a notion that's going to keep showing up really all year. You're going to get very familiar with this definition, and it's linked to like a lot of other really important results. Like there's going to be a lot of theorems and things that start off this year where it says, given a set of n linearly dependent vectors, or maybe it'll be said n linearly independent vectors, so and so and so happens. But what it basically says is this set of vectors is going to be dependent, linearly dependent, if you can find scalars where just at least one of these is non-zero, such that you can add scalars of them up like this and get the 0 vector. So you only need one. Like you could have just C1 be non-zero, and then you could have C2 through CK be all 0. But as long as you can find one where it's non-zero, then if you figure out a way to add them all up and you get the 0 vector, that means it's dependent. And that definition, to me, makes a lot of sense because I've worked with this for a long time, but there's actually a theorem that I always felt like helped me understand this definition better. And so I'm going to show you that in a second, but I think it's good to see an example, more like an intuitive example as to why these vectors are not linearly independent. So these ones are dependent. And really the issue is with the last two. So these two right here are scalars of each other. And really, if you ever find one that's just a scalar of another, then they're parallel vectors, right? And that's actually going to be, that's going to mean that they're dependent. But to formally show it, we want to show that you can add, I'm going to call this V1, I'm going to call this V2, I'm going to call this V3. So I want to show that I can add V1, V2, V3 and get the 0 vector somehow, given at least one non-zero scalar. And so I'm going to do it with, I'm going to take 0 v1, and then if I add v2, right? So right now I'm at like just the vector 2, 6, because I took 0 of the first one. If I just subtract 2 times v3, right, then I would have the 0 vector, because I would take away 2 times 1, 3. So, you know, if I follow this kind of pattern where C1 goes with V1, C2 goes with V2, basically, I'll do it like this, C2 and C3, I showed, I guess, there exists C2, C3 that don't equal 0, such that C1 V1 plus C2 V2 plus C3 V3 equals that 0 vector. And that means these are linearly dependent, so they are not linearly independent. Intuitively, it just means, the vectors are not pointing in different directions, really. Like, these two vectors right here are scalars. This one's just 2 times this, so they're parallel vectors, and they're going to point in the same direction. In order to get 3 independent vectors, you've got to have them shoot off in different directions. Like, you could take I, J, K, and, those are linearly independent because none of them are scalar multiples of each other. But if I have, say you still think of that in 3D space, if I took half of I hat and I threw that in the mix now, then I have dependence, because this yellow vector, which I'm just calling half of I hat, is a scalar of I hat, and so it's just like these vectors right here. And so this is the theorem that I think makes some more sense, that really shows this idea of dependence, linear dependence with vectors a little bit better. And so I want to prove this. So this says that given a set of m vectors in Rn, linearly dependent ones, that happens if and only if you have at least one of the vectors can be expressed as a linear combination of the others. Okay? So if it's one of these if and only if problems, I'm going to start and prove like the forward conditional. So I'm going to assume that V1, V2, all the way up to Vm are linearly dependent. That means, by definition, just from before, we have that C1 V1 plus C2 V2 plus blah, 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 Cm Vm equals the 0 vector. And we will show that V1 can be written in terms of the others. And you could do this with really any vector, so it doesn't have to be V1, it's just the one I'm going to do. But you could, without like loss of generality, you can absolutely do this proof where you could write V2 in terms of the others, or VK in terms of the others, or VM, or whatever, but it just kind of makes sense to do V1. If you have this statement right here, which is my linear dependent definition, then what I'm going to do is I'm just going to subtract everything but the C1 V1 term to the other side. Okay. So let's see. I know C1 V1 equals minus C2 V2 minus, just going to do ... minus Cm Vm. And I can divide by C1, and likewise, then V1 equals minus C2 over C1 times V2 minus ... minus Cm over C1 Vm. And that basically does it, right? So now I've showed the way that we write v1 in terms of the others. These right here are just the from your original coefficients. If you just divide them and negate that of v2, and then you keep doing that all the way through, if you subtract all those, you should get v1. Basically, it's just the idea that I can write v3 as 2 times v2. So I can write v3 in terms of v2 here. That's the idea. And to prove the other direction, it's almost quicker and easier. We could just assume there exists some vector that can be written in terms of the others, and we prove it is linearly dependent. So I'm going to start with v1, which equals like c2v2 plus blah, 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 plus cmvm, all right? And it's really short. Basically, I'm just going to subtract v1 over, and I would have this. And that really does it, because you have shown that there exist these coefficients that are non-zero, right, that add up and give you 0. So, basically the idea is since C1, which we're basically saying is -1, doesn't equal 0, it's non-trivial, this proves the set of vectors is linearly dependent. And that would be the proof. You just have to show that there are these coefficients that you can stick in front of the vectors and get the 0 vector. And it doesn't matter what C2 and Cm are here, as long as we have this -1, then we're good. That's going to give us the 0 vector. So these are just some sort of important concept questions. So any set of vectors that has the 0 vector is actually inherently dependent, because you could just take 1, maybe I'll even write it, 1 of the 0 vector. Then I can add like C2, it doesn't have to be anything, of V2, C3 of some other vector, however many vectors you got. And no matter what those other vectors are, you can get this to equal 0 if you just let C2 all the way through Cm equal 0. You just need to show that there is at least one non-trivial coefficient to get linear dependent, and you just take that to be the one in front of the 0 vector, and it's just equal to 1, right? 1 0 vector is basically then going to equal 0 vector if you have this line in red right here. We already sort of talked about this. So two 2D vectors can be linearly dependent basically if one is parallel to the other, or in the sense of vectors, like v1 equals some scalar of v2. Basically, so like alpha is like something in the reals here. But you just need one to be a multiple of the other, and then you're going to have those vectors be linearly dependent. And then this is just to show you again, like, so don't think that they necessarily are going to always be super obvious that they're dependent. Like these ones here, it's not like I have this thing times 2 right here and then they're dependent. What you should see here is if you basically add across all the rows, you can get the 0 vector. So sometimes you have to be kind of clever with how this works. So if you just take one of this vector v1, and I'm going to call that v2 and that v3. If you literally just do v1 plus v2 plus v3, it will equal the 0 vector, because the x component from this one cancels the x component here, the x component here, y here cancels y here, and z here cancels z here. Now there is actually a very concrete kind of way to do this, and that's like the last thing I want to show you here. So what I want to show you is, if you have this set of vectors, this would be much harder to show whether it's dependent or not. The idea is like, you want to take some combination of one of these vectors, and you want to add to it some combination of the other one, and add to that some combination of 1, 2, 0. And you want to see if you can get 0, 0, 0 out, right? And so basically what you do is you make a coefficient matrix. You just try to solve the matrix 1, 1, 1, 0, 4, 1, 2, 0, 2, negative 1, 0, 0. And if you just solve this, and it has a solution, then it tells you what C1, C2, and C3 are. So if you RREF this thing, you will get 1, 0, 3, 0, 0, 1, negative 2, 0, and then a row of zeros here. And if you think about what this line says, it's basically saying C1, right, equals negative 3 C3. This line says C2 equals 2C3. And so if you just let, really, C3 is a free variable here. So you could let C3 equal anything you want. You could pick 1 for convenience sake. So then you could do C1 needs to be negative 3 of C3. So you could take negative 3 of 1, 4, 2. And if you add that to 2 of 1, 1, negative 1, and then you add that to 1 of 1, 2, 0, then that should be the 0 vector. Let's just check like the top row. So this is negative 3, plus 2 is negative 1, and then plus 1 is 0, right? And you can go through and check all the others if you want. But basically what I write right here is the idea. You just need to try to solve the matrix problem, like whatever the coefficient matrix is for the vectors. So just pulling these vectors, making them the columns of the matrix here. And then you augment that with the 0 vector right in this last column. And basically, if that has a non-trivial solution, then that would prove dependence. The only way you're going to get independence is literally if your RREF matrix looks like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And that would mean this is saying C1 equals 0, C2 equals 0, C3 equals 0. And so then it means that there's no way I can stick non-trivial numbers in front of my vectors and get the 0 vector out. So that is basically the only case for linear. I should probably write that. This right here is what RREF looks like for linearly independent vectors. I guess at least a set of 3D linearly independent vectors. If it was a higher dimensional vector, you would basically still get that row of 1s going down. It just would have more entries, right?